Hello, today I want to talk to you about radical reactions. I want to go do an overview of bromine radical reactions and tributyl tin radical reactions. And so we have just an overview on the board. These are the three radical reactions we're going to be interested in this semester. We talked about them in class yesterday. I want to give you an overview just as you think about applying these to different types of problems. So the three types of reactions we're going to do are reactions where we use HBr, and again, HBr can be either a polar reaction, which you learned last semester, or a radical reaction, depending on the conditions. NBS, N-bromosuccinimide, which is going to be a different type of bromine reaction. And then tributyl tin hydride, which is going to enable us to form carbon-carbon bonds. So if you look at this table, this highlights sort of the overview of what's going to happen in these reactions. So with HBr, we're going to add to a carbon-carbon pi bond, so an alkene. We're going to generate a radical intermediate after adding bromine to that alkene. And we're going to form two new bonds, a carbon-bromine bond and a carbon-hydrogen bond. When we do a reaction with NBS, we're not going to add to an alkene pi bond. Instead, we're going to react with an allylic or benzylic CH bond so that we form a resonance-stabilized radical intermediate. And then we're going to form a carbon-bromine bond from that resonance stabilized radical intermediate. When we use tributyl tin hydride, we're going to break two types of bonds. We're going to break first a carbon-halogen bond, then a carbon-carbon bond. The radical intermediates are all going to be carbon radicals, and we're going to form a carbon-carbon single bond. So this is going to be very helpful to us in synthesis problems. So now I want to just go through each of these individually so we can highlight the important parts of these reactions. So when we do our HBr reaction, we're going to add HBr to an alkene. So we're going to do a reaction that looks something like this. So if we have an alkene like this, add HBr to this. Again, we've done this reaction with polar conditions. Here, if we have some sort of radical initiator, right, we'll often see some sort of peroxide as our radical initiator, just something to get radicals forming, then to react with HBr, we're going to end up generating that product, okay? And so we need to make sure we understand the mechanism of this reaction so that we can do this for other cases, right? So the first thing is that we have some initiator, and that initiator is going to form some sort of initiator radical. And we did peroxide in class. Doesn't really matter what that initiator is, and that's why I'm just writing it as generic initiator. React that with HBr, and we're going to form a bond from the initiator to hydrogen and Br radical. And as we talked about in class, Br radical is going to be our chain propagating radical. That's going to enable us to do our radical chain reaction. All right, so let's look at what our mechanism is going to be. All right, and in that mechanism, we're going to start with Br radical, which is our chain propagating radical. All right, and the key here is that we're going to have Br radical add to an alkene first to form the most stable radical intermediate. All right, that's the key part of these reactions, understanding the mechanism. That's the key. All right, so for this reaction, if we add in our alkene starting material, bromine's going to attack at that position so that we generate a tertiary carbon radical, which we've talked about is going to be much more stable than a primary carbon radical. More substituted radicals are more stable. So that's our first intermediate. And then we can regenerate our chain propagating radical and generate the product if we react that carbon radical with HBr. So we're going to form that bond. And again, we're using single-headed arrows to indicate single electron movement, not two electron movement. right? That's the key difference with polar reactions versus radical reactions. And so that will regenerate our chain propagating radical and give us the product. Right? So that's just a generic HBr reaction with an alkene. Now, if we think about the NBS reaction, right? In NBS, we're going to form allylic or benzylic bromides. Right? Very, very useful reaction. You can take something that's just an alkane next to a pi bond benzene ring, turn it into a bromide, then you can turn it into a Grignard and do more chemistry with it. You can do an E2 reaction next to a benzene ring. There's lots of stuff that you can do. We have lots of reactions of different halogens. So this is going to be a very useful reaction to us. If we take the same substrate, NBS with heat or light, what will happen is the alkene will stay and we'll just add bromine in the allylic position, which is a really nice complement to the reaction above. Okay, very interesting that we get different reactivity here. It's important for us to know what the structure of NBS is. N-bromosuccinimide, right? That's NBS, right? And when we shine light on it or heat it, we break the weak N-bromine bond, and that generates Br radical. Right? And it's very interesting that this reaction undergoes a different outcome and we're using the same chain propagating radical. So this one is very dependent on the chemistry of NBS to control this reaction. So we make a low quantity of that bromine radical. We'll also see that key to this reaction is forming Br2. Right? So this is a very interesting and unique reaction. It's important for us to remember that. Right? So when we think about the mechanism of this, it's a combination polar radical mechanism. It's done very nicely in your book. I'm just going to do some of the key mechanistic steps. I'm not going to do the entire mechanism. We'll do the key mechanistic steps. So when we have Br radical in this reaction, right, we're going to generate a different radical than in the reaction above. Because what's going to happen here is we're going to abstract an allylic proton to make a resonance stabilized radical. Right? So we're going to end up with, right, a radical that looks like that. And again, it's resonance stabilized. Okay? So we've made a very stable radical because it's resonance stabilized. The interesting thing is that this HBr that we form, that reacts with NBS to give us Br2. Br2 is what's going to react with this resonance stabilized radical to generate more of our chain propagating radical. So we have Br2 coming in here. And so this radical is going to form a bond and give us the chain propagating radical back. And this gives us, we'll just add this arrow over to here, that gives us our product. Right? And you can note that we have two resonance structures. So if this isn't a symmetrical allylic compound, we can get mixtures of products. Right? So that's important to note. So again, two ways that make a carbon-bromine bond, one that we add to the pi bond, one that we add next to the pi bond to make an allylic or benzylic bromide. Right? And let's erase this, and then we'll finish by talking about making carbon-carbon bonds. So for tributyl tin hydride, we're going to use this to make carbon-carbon bonds. All right? So this is CC bond formation. Very, very useful reaction. So for example, this is a really nice way to make rings. And when we react this with some sort of initiator and tributyl tin hydride, we can make, in this case, a 5-membered ring. Very powerful reaction, right, where we're able to turn some sort of bromide with an alkene into a ring, right? And we'll see a lot of examples of this in synthesis, right? And so when we think about what happens here, same deal as before. We make some sort of initiator radical, react that with tributyl tin hydride, and that's going to form tributyl tin radical, which is our chain propagating radical. Now, when we think about the mechanism of this reaction, there's an extra step than in our other reactions. So our first step is going to be to react this with a carbon-halogen bond. And that's the key thing. The first step is always the tributyl tin radical reacting with some sort of carbon-halogen bond, right? And that's going to generate our carbon radical. Okay, so always look for that carbon-halogen bond when you're doing reactions with tributyl tin radical. So we're going to form the carbon radical, and we'll also form, in this case, tributyl tin bromide. All right, so we form our first carbon radical, and when you form a carbon radical with an alkene that's positioned appropriately away to make a reasonable size ring, so in this case, if we make that bond, we're going to make a 1, 2, 3, 4, 5-membered ring. Right, we can make 5, 6, and 7-membered rings very nicely using this strategy. That gives us 5-membered ring, secondary radical, and then this can react again with tributyl tin hydride to give us our product and regenerate the tributyl tin radical, right? When we think about ring formation, which again is a very powerful application of this chemistry, 5 forms faster than 6, 6 forms faster than 7, and 7 forms faster than 8, right? And let's say this is, generally true. We will definitely see exceptions to this, but in general, if you have to decide between making a 5 and 6-membered ring, you'll go 5, 6 and 7, 6, etc. You'll note in this case, we could have formed a 4-membered ring if we had added the radical to the other side of the alkene. 4-membered rings are not stable enough to form using radical chemistry. So we're generally going to form 5, 6, and 7-membered rings. Right, so just to summarize, for radical chemistry that we're interested in, we're going to make carbon-bromine bonds and carbon-carbon bonds. And we have 3 reagents that we use: HBr, NBS, and tributyl tin hydride. Right, if we can be comfortable with those reagents, then we're going to be in very good shape to solve the problems we're interested in.